First of all, I would like to say thanks to the rest of the committee here and also to John especially for inviting me to give a talk. And the topic he gave me was global ice fracture experiments at Spitsbergen. I added a little bit more into the application of it. On pure science, it is of course important to do that on the basic level and look into it, but for us we also have to look somewhat into how does that impact, for instance, estimation of loads on structures in especially the Arctic. I have also with me postdoc Wenjun Lu, and there was no slot for him in the program here, so I give him let's say 10 minutes at the end of my talk, if you don't mind, John, to look somewhat into what he's doing start with some analysis. I'm based in Trondheim and leading a center called Sustainable Arctic Marine and Coastal Technology. It's a so-called research-based innovation excellence center. But another thing which is quite important is that I have a connection to the University Center in Spitsbergen, UNIS, which is located at 78 North and give us excellent opportunity to do field work out from there with the UNIS as a base. My talk is divided into some motivation here and then test design related to this test we are talking about here on sea ice in the area close to, not close, but somewhat from Longyearbyen at Spitsbergen. I will then talk about the field tests, some preliminary results, and somewhat into applications. So let's go a little bit into the motivation first here. This is typically what I feel is important to stress a little bit. If we think about what we meet in the Arctic, I have seen a dramatic change. In one of my field trips, actually in 2016, I was not able to land with a helicopter east of Spitsbergen because we have a requirement there on the ice thickness of 40 centimeter, and it was hardly that. That's the first time in my life I've really experienced that of a situation. What does this mean and what does it lead to? We see that there is really a thinning of the ice cover in the Arctic, which means that gravity waves are more able to penetrate into the ice cover, and instead of having much the condition you see here with continuous level ice and so on, then you have much more what we call floe ice. Broken ice in either by the gravity waves, as I mentioned, or due to operations. Like you see here, in this case, we have a vessel which is supposed to stay in position. We call it on DP, dynamic positioning. It could also be on mooring, but in this case on DP. So the thrusters has to compensate for the load you get from the ice on you to stay in position, and you cannot deviate more than typically 10% of the water depth. So if you are 300 meter here, 30 meter out is the radius you can allow yourself to deflect from the set point. And then it's important to be able to, let's say, handle the ice which comes upstream. The drift is supposed to be in this direction, with the larger flows up here and maybe a second icebreaker, breaking this down to what's capable of handling with the capacity you have. Just a slide from the Arctic Ocean. We are now up at 82. This is in 2015 with Odin, and you see even up there with an ice cover here, 700 meter wide and 1.3 kilometer long, just broken ice, and we are in the Arctic Ocean. You also see this from some of the trips to the North Pole. And if you go back in time, this is a reference to Rotrock and Thorndike back in 84, 110 kilometer and 95 wide, quite some broken ice there, although this is then summer conditions referred to. So on these various expeditions we see and so on, we have also to consider the interaction with the structure we are discussing. That could be a vessel, as in this case an icebreaker or ice-going vessel, or it could be a structure which is more composed of let's say several legs, like whatever, where the interaction is major for what happens of load, and you have to design for it. So what can we then see? We see much of different failure modes here, not just one. And if you look at the hull here in the contact zone, you see that we have bending failure of the ice. We do also at the stem here have some crushing. And in addition, there are splitting and circumferential cracking. All these things coming more or less at the same time. And you see crack running forward as you see here. So if I take an example here from Odin in ice, you see a floe. This is 108 meter long, this icebreaker, so the floe is 200 plus. And what can you see when you are breaking forward here? You see a crack developing here, you see another one here. But what you should also recognize here is that there is a lack of confinement on this floe. Which means that in the interaction zone here, the stress field must see or get the feeling of the boundary conditions clearly. In addition, we do have a local bending failure, as you see along the reamers here on the vessel. So I would say that the conventional local bending is accompanied with frequent splitting failures, as we see. And it also, and I'm more and more convinced about this, that fracture mechanics is a natural choice for the failure mode here. So it's more and more important. And in our case, we are talking about this from the perspective of sea ice, which of course has salinity. It's more porous, of course, than freshwater ice and so on. On this slide, you see the bow of the icebreaker, and what you will see in the next seconds is a crack running from the bow here when we run into this floe and strike forward. So to let you understand, this is a bow camera pointing forward, similar to what you can see here. This is not the same crack. I run it once more so you can better observe. I haven't exactly estimated the speed of the crack here, but we are more than 10 meters per second. I think we are talking about 15 to 20 meters per second on this crack running. And what was characteristic and what I said was that there is lack of confinement on this. It was just as you saw on the previous slide. Now we are running into it. And you hear the rattling. Can you hear it? And then we come. The temperature here is low. This is up in the Fram Strait in 2012. But what I would like to say and stress, I see this kind of failure both in cold ice and in warm ice. So even if we had minus 30 here, this could very well happen at minus 5 and minus 8 and so on as well. So that's what we see. If I go to this slide here, this is from a publication I have together with Professor Carl Schieneck. Unfortunately, he has passed away in 2006, and this has been adopted by ISO 19906, Arctic offshore structures. And what is nice to see here, we outlined what affects ice actions like ice features, ice properties of course, and then we have this limiting mechanism. Interaction geometry is important and failure modes as well, for sure. What I've added on this slide here is limit splitting, because ISO contains stress, momentum and force, but we clearly see that the splitting should be in there. So what concerns me with ISO, and I'm in one of the working groups there together with Bob, Fredriking and others, is that if you now think about loading from this kind of perspective, say that you have a probabilistic approach here and you have a certain parameter which affects you, a distribution of that one, another one, a third one, and so on and so on, and you need to put up create a parametric model here. And what is there is very often that you take a deterministic model here, which include one failure mechanism. So it means that you go back here and you choose a failure mechanism, and then you start calculating for there. And that's completely wrong according to my vision and understanding, because that's not what we see. We see the combination of different failure mechanisms at this more or less at the same time. So I would say the problem with ISO here is they have no proper model here considering that. And I will not go further into details here in this talk here, but it's for me it's at least a major concern. But however, when we talk about ice and fracture as we are doing here, ice is a rather complicated material. That's clear, and we know that quite well. And if you also look at cohesive laws and so on, or three parameter cohesive law with fracture energy and tensile stress and crack opening and so on, displacement, then we do not agree fully on this for sure. And among these in the discussions, we have size effects, which we discuss. How much can we rely on what we see in lab compared to full scale and so on? How well can we do things in full scale? That's another part of it as well. And then also loading rates. Is there any dependence there or not? And so on. So there are many things to discuss, which I will touch upon. So the test we were doing, I will go a little bit into the test design. First of all, you have to consider size requirements here. Like you have a length in the cleavage direction of your test divided by an average grain size, for instance, exceeding 200. I think that's common to say that it should be more than that. We could also think about the length here in relation to the characteristic length as you have, and could relate to this if you refer to Mulmul and Demps in 2000 and so on. This is typically what has been considered there. So when we were designing the tests, we were looking into simply going with a lower and higher value for the fracture toughness here, leading to lengths in this scale here, or if you go for a higher value, this is by Erland, and this is by John, for the fracture toughness, and we take a relatively conservative value here. We would say that we need at least 3 meters for our experiments if we should think in this direction, as we should. When it comes to the loading rate, it's a little bit the same of considerations here with speed of what you should apply, and we went for different ranges here because on beforehand we didn't know exactly what we could need, for instance of temperature in the ice and so on. So here is a profile of a typical temperature we had in the ice, which in this case for these tests here were about 60 centimeter thick. So another thing I would like to say is also that I'm very much in favor of a stiff system when we are testing, and we know that there are several jacks loading system based on hydraulic system. If you should that properly, you should probably need to have a closed loop for the feedback and so on. So I've always gone for screw jacks with a high capacity, for instance from this engine here until the loading device, which is below here. We have a gearing of 1400, so I actually could turn this more or less with my finger, and in that case I know it will be quite stable in the speed, or I could say independent of load. So we had speeds here from 0.015 millimeter per second to 0.6 to 1.5, so a factor of 100 here from the lowest to the highest. So what about the field tests in itself? I mentioned Spitsbergen here. This is the island, and Longyearbyen is located in here. And our test site was in the south here, about 60 kilometers from Longyearbyen, so we have to drive with scooters over here and do testing here. If I go 15 years back in time, I could have done tests here. But due to what we see, whatever it's global warming or what, or the cause of it, I don't discuss, we see that we have no chance to do proper experiments here longer. I mean, we have no stable ice during the winter. And we did even go further, because driving over and doing experiments here in this area, we went into this lagoon, and it has exactly the same salinity as the sea outside, about 34 parts per thousand. No rivers coming and flowing in here, of course. Then we have really stable conditions, which we were heading for. So to come to that site, it looked very much like you see here, snow on top, and you need to perform something here which is both efficient and also reliable, and also considering safety is quite important for us. So here a little bit of the team. I think you can recall Yuka and Wenjun and John Dempsey. That's a part of the team which was there in 16. We started in 15, but we have some failure in the system there. So it was first in 16 we got proper results. And we can also add the team in 2017 with the equipment we applied. So how did we do the experiment? I always in favor of having things where you don't need to rely on equipment that should be submerged. So we have a special design jack where everything related to the loading rate and measurements and so on were above water. In front, so made a notch here in the floe and lowered the jack in so it could expand. I will show you that a little bit later. Measurements was done of the crack mouth opening displacement here, and also what you have in, but also at the crack tip. So by keyhole test we know relatively well where the crack would go, and we did an experiment, and that was the way we designed it. I mentioned this and I would also like to stress another thing. The device did not load the flow here. We had a crane up here, and we all have some wires going or ropes going back, so we were sure that we didn't impact or affect the loading there on the flow. So if we look at this jack, 2 plates, 200 meter high and 150 wide, jack working here, and also a load cell, so we could just easily lower this into the ice and start the experiment. It's also a matter of time. If you have an experiment which lasts very long or a slow procedure, you will definitely, after cutting the notch and preparing for the experiment, affects the thermo or the temperature in the test area you are imposing to apply. A little bit from the preparations, doing certainly after some experiments prior to this, developing a jack here where you have the loading plates, and you see we could just pull here instead of push, and then we got a steel structure which we designed in order to be efficient here. So what about the execution here? Removal of snow, that's the first thing, of course. You need to have a bare surface. Different sizes, I mentioned this with the size effects if we want to study. Then also cutting sequence, as you can see here. Typically this is 5 meter in the crack direction and 10 meter wide on the other side. And as I say, it is important to have this in such a way that you can do it relatively fast. A test was typically run about within 2 hours after cutting here. And you can also wonder why we could be so effective. I'll come back to that. Here you see this from another perspective. And the instrumentation. So, first, cleaning the snow. Jukka volunteered here, doing quite well. But the most important here was something, the idea we stole and borrowed, and we are really grateful for that, from John, ditch witch. Because this was the major thing for us, which means that we could cut the ice at the speed of about walking here. Here is a device. We could pull this with a scooter over from the land area over and in here. It's 520 kilo, and we could do it safely. Chains on and so on. So that was really great. Then, prior to we start the real testing, we made a notch here for that is a notch for not for the crack, but for the jack to go into here. A keyhole is made up here, and we were ready to do our first experiment. This is back in 16, in order to see where we could expect the cracking. Where would we expect the z-axis to be, or the basal plane, and so on. Another important thing was this device we had developed for measuring the crack opening when it starts, when you get the stress out here and you start running forward with the crack. So a neat device here installed, mounted on wooden sticks in the ice and frozen in, so it was quite stable. What about the instrumentation? Data logging in 16 or 50 Hertz, we found that was could have been better, so we increased this to 1000 Hertz in 2017. We had loading rates from 0.015 millimeter per second to 0.6 and 1.5 millimeter per second displacement here. And the jack here is in place, lowered down, and it's ready to run one of the first experiments. Here is a little bit information on the displacement sensor. We were discussing a lot there whether we should use optics, but we know that in Svea it's a damp place in relation to wind. That means blowing snow along the surface, so that would be disturbed. So we went for a different device here, well protected, and that was a success, I would say. Success and success, we do always have to pray a little bit before starting, and Wenjun was hoping the very best, as you can see here. What is the video? There's a video before this. No, I can put it in the previous one. Okay, I think we run on because I see that time is passing. Yes, and then following up on the instrumentation is of course very important there. So with a little bit less light, but I think still you are able to see crack running through the gauges here and up to this point here in this case when I took the photo, and later on it would proceed. But we could also stop a test, of course, in order to, let's say, capture, for instance, the crack tip. An example on that, this sequence is the following. We have a stable crack growth all the way. In this case, we stop the test, and this is not a keyhole test, by the way, for those who may think so. This is just a sample, 4-inch, taken out from this section here, and what you can see, but it's not taken out here, is the crack tip which stopped here when we unloaded or stopped the test here. We didn't unload, we just stopped the test with the crack tip included, as we may consider here. So what do we see there? This is the core which we have just pulled out here, and so you see the skeleton layer here, which is the lower part of the core, and we have the top here. So if you put the goodwill in here, you can see that you see the crack here all the way from the bottom here to the top of the sample. And this didn't, we stopped it just before and put the drilling in such a way that we kept this as one piece. So now we have a vertical core which we have just taken up here with the crack in, and then just put it on the ice and make this photo. So this is the core which was taken out from here.
Before you start the experiment, did you do anything to sharpen the tip or?
The sharpened?
Yeah.
Yeah. I think I'll come back to that in a minute. If not, I will tell you about it. So what can we say here about preliminary results? If you now take as an example, okay, I should probably immediately answer to your question. What we did here, if you see the jack is here, I can look at this one here, and the distance over here is 5 meters. So we used the ditch witcher in to a certain distance. Then we used a chainsaw a little bit further, and then we went over to a handsaw, which was about 1.11, around 1 to 1.2 millimeter wide. And of course, it's very, very important that that is sharp, as we were considering. So there was no way you could run this all the way. So we stopped well before we were afraid of interrupting the whole thing. Wenjun, do you know where the video is on the? What? Okay. So that was about the notch. Yeah. So what you see here now is another core taken from the core tip, including the crack, the crack tip. Sorry, and you can clearly see this displacement sensor being measured over the crack, and of course also where you have the loading device. For the result you see now in a few minutes, we have a loading rate of 0.6 millimeter per second. And in this case, we have a crack, the crack tip included in this core. So it's the crack or the core sample we have taken from what is indicated on the photo here. We know, of course, if you start going back to theory here and so on, if you go to microscale wherever all the way down, you can consider the fracturing as breaking of bonds, either it's covalent bonds or hydrogen bonding and so on. And typically, if this was an ideally brittle material, you could have this as the fracture energy here related to the surface energy plus multiplied by 2. But when we talk about a more plastic material, and we can't expect that sea ice is ideally brittle here, you more have to consider that there are things happening in this area here, which is not just related to breaking up that ice you have. You have pore water in there. You have a porosity, which can be also relatively high in sea ice. So it's quite, I would say, quite complicated. So here is, from the core you saw now, here is X-ray scan. I think that this is from the core you saw, this previous slide. That means from the very top here, which is behind this cage here. We have captured the crack, but this sample here didn't capture the very, very tip for the one we run X-ray on. But I will show thin sections where we have that in. So Z is equal to 0. That means we are on the surface. We had access to a chamber here, diameter 8 centimeter, and a sample size in this case of 8 centimeter over here. run then at -20, and this is of course in the lab at home. And here we could slice up with 2D images which we put together into a surface which tells us something about the crack development and the crack surface. So by 2000 pixels here, we have a resolution of 14 micrometer. And the revolution here is then 0.1 degree for each slide we have in here. So from this, we could get a 3D model, as you can see here. This is what we then obtained from the X-ray test. The crack is running from this way and out there, and this is the vertical, to make this clear. If we remove the ice, which is possible to do, then you get this kind of image here, where you have the crack going clearly down here, and you see it's absolutely not the plane surface, and that can probably be a difference in freshwater ice. You have less impurities, you have less pores and brine pockets in there, so I would expect that could be more plane. So it's developed all the way over here. What you can also see is that there are quite some inclusions here of brine pockets in and air pockets as well. So there is a complicating factor. That's nothing to discuss. That's quite clear. If I now take this sample and then take a layer, integrate over 2 and 2 centimeter down the way, you will see a video now where you can see that. So the video will see now going down from the top of the sample here down towards the bottom of that sample. And what you can look at there is details. If you look here from the top here, you see the crack is running in this way here up through the sample, and you can see here this is clear, the crack is going here, so this is magnified here, and you see also 2 lines going here, so this is a bifurcation here from this point and over here. And you certainly see that this follows weak sections, weak parts of the ice where you have, for instance, brine pockets. We could take another part of this, magnify it as you see here, and you can see the same tendency here. So if I now go layer by layer, 2 by 2 by 2 centimeter down, it will look at, as you see here, okay, the crack is going here. You see also the brine pockets coming up and gas pockets and so on, but the majority is that we clearly can see that it's not fully continuous here. You have certainly surfaces here that are intact in some way to some level, but then it's broken off in other places and so on. But in totality, of course, you have an opening here. You have an opening here, so it has to be broken. And another thing I would like to say is that if you look at a crack like this, now to magnify it a little bit, and now we are diving down, that's what you see there. It is clearly that it's not straight as you think here. You see also deviations here at the crack tip. So just be aware of that. So if you take just one thin section, it could be from the top here. It's not the whole story. Be aware of that. Then if we go and look a little bit at one test here for that could be some thick and thin sections. You see this year and it was actually the same in 2016. The temperature in the ice was relatively warm. We can say that we have an average here of around maybe minus 4 or so. The jack was located here at this surface at this depth, 30 centimeter below. And if you look at this test number 9, we had a rate there of 0.6 millimeter per second and corresponding to 100 kPa square root of meter per second. we can look a little bit more into that. And first of all, I would like to thank Jukka Tukuri, sitting here somewhere. You made this together with Krzysztof, and this is not a thin section, it's a thick section, okay? And when I say Z equal to 25, it means that this run from 17.5 to 20.5 centimeter measured from the top. And the top is not here. Remember that the top is over here, okay? Yes. So what can we see here? What is captured in this photo here? We see the crack is coming, running here from the bottom. The bottom means, sorry, from the bottom of the photo. It's running like this, and the test was stopped, or it was stopped in such a way that we have captured the crack tip, as you can see here. And you can also clearly see some of the porosity here in the ice, the brine pockets and so on. So what I can see here is that you can see that ice are fully in contact on sides here. So what can we say here? Thin section obtained from an ice sample included a crack tip. We interrupted the test, as I say, and we can clearly see this crack being open from this way and forward over here. At this we will also look at a thin section going from thick to thin section. And again, at this depth of minus 20 or at 29 centimeter from top down, you can see in this thin section here clearly the crack running over here. And also you can see probably that it diverts a little bit, go around, and so on, clearly seeking for weakness in the ice. This is very close to the crack tip, so the crack tip is up somewhere here. And we also see that it's not fully continuous the way we see it on this slide taken here. A little bit more information. You see it's quite open here, and it's clearly that you are following pockets in the ice, or weak zones in the ice. And you see here it's not bifurcation. I think we have 3 going and coming back together in here and running further up. You can see more clearly the grains on this slide. Or if I go into this one, you can more clearly see the grains here. I haven't had time to calculate properly, but we are in the range of 3 to 4 millimeter average size of the grains. There's some statistics here. This is not diameter, this is grain area which is used. And then we do of course have also information on the orientation here. If we look more closely here, we see the platelets. You can see that this is 1 millimeter over here, and we are now at the same depth. And in this case, where this thin section is taken from, we can see that the crack has been running over here, so actually transverse to over the platelets here. But we can also see that it's refrozen. It's healed. As you can see, we have no more or less solid ice here, so there's recrystallization. If we look into this slide here, we can also follow the crack going around and up here and so on. So as Krzysztof said, crack looking for discontinuities in the ice here. So of course this must be very different from fresh water ice. There's no question, and that you can see here as well. If I take these microscope observations and look, we are at the same depth. We can see the crack running over here, and here this is a void, a brine pocket, or could be gas as well, running further here, forward here, and up, and probably looking for a weak zone. What you can also see here, that the grain boundary here is clearly transgranular. So it doesn't necessarily follow the grain boundary. And we could start looking into the same here. I think that you could get some minutes now, Wenjun, if you don't mind. And then we take the questions afterwards. But I will stay within the time, okay? By the way, there's a break afterwards, so it's not so strict. These data are so fresh also that we always say here preliminary results. We have not published them yet and so on, but of course it's coming. Jeroen?
Yeah, I have a question concerning your observation on X-ray tomography, your very complex shape for the crack, but could it be related also partly to some healing mechanisms between Svalbard and the X-ray chamber?
For the X-ray, we kept this code all the way.
Healing.
So, yeah. Okay.
Thank you. Thank you for having me here. And I will, after Sveinung have been dived into these microstructures, and allow me to bring you to surface up to see what we measured macroscopically about the load and the displacement. And at first, I would like to make a conclusion about what we have done so far. It was, we had a successful 2 consecutive years, 2016 and 2017. And in 2016, we had 17 ice floes which were fractured with the same rate. And all these ice floes covered 3 different sizes, 3 meter by 6 meter, 5 meter by 10 meter, and 10 meter by 20 meters. Still, we haven't yet exceeded John's record, which is 80 meters. But we believe these sizes are enough to extract the information that we need. And in 2017, which is early this year, and we focused on the loading rate. And we again fractured 17 ice floes with 3 different loading rate. And this loading rate covers approximately 100 times different. So we want to see how the size affect our results and how the loading rates affect our results. This is the general overview. And I saw in Jeroen, your presentation, you have 16,000 fractures, right? And for us, we have only 34, but it took us 2 years to achieve this. Okay. At first, about the size effect, we will just focus on this particular geometry, 5 meters by 10 meters. And the initial crack length is about 60%, which is 3 meters. And these are the peak force while we load the sample, and the force increase, and then it fractures. And we recorded this peak force and then plotted here versus the size. And they are all of the same loading rate. I made a simple calculation based on linear elastic fracture mechanic. This is just to show you the geometry. There's nothing else behind it. And after I plotted these things together, and I cannot hold myself to plot this simple line here. This is if it follows this linear elastic fracture mechanic, then this L square like a minus 1/2. This trend. Is this really following LEFM? There is some scatter. I don't know, but I will just continue present, and later I'll make a preliminary summary about this. In general, it looks good that it seems that they are following this inverse square root trend. But are they really linear elastic? If we go to the force and displacement, here this figure is a bit busy, and it essentially encompasses 3 different loading rates. So this is force, this is displacement. So this is the displacement at the crack mouth. So that's why we see the displacement is relatively large. And first, these 2 very thick ones, they are the slow loading rate with this very small, slow loading speed going up, and then it goes down. And initially, this was the test number 2. We were not well prepared. Let's say not to really. So we stopped our test here. But later, later we realized that the tail is also very important. So in the test, we keep data recording and going until it's finished, almost level up. And this is a slow loading. The same sample, 5 by 10 meters. and the force is relatively large. Then we try to do it faster with the immediate loading rate, which is 50 times larger, and then again 100 times larger. And we see that it seems as we go higher speed, the load peak is decreasing a bit, but it's not always the same, because we see an anomaly here with fast loading, this dark curve. This dark curve is a bit higher together with this immediate loading, so they are a bit inseparable. And the question here is that are we able to describe this loading path with linear elastic fracture mechanic? At the first look, it looks okay, but if we try to zoom in this part, we see that it's really kind of curved. And whether or not we can use the linear elastic fracture mechanic, I don't know yet, but it doesn't look really perfectly linear going up. And also we see that it seems that there is a loading rate dependence on the peak force. That's a bit puzzling to me. I don't understand why if we load it slow, it seems that we get a high peak force. If we load it relatively fast, we get a low peak force. And at first I thought maybe this is because of some additional energy dissipation mechanism going behind there. Like Alan in his paper, you mentioned about that. I think other people also mentioned that if it load fast, and you get a relatively lower force. If you load it slow, you get a higher force. But you are talking about fracture toughness in that paper, and this is something like we got from what we measured. But what's puzzling me is that in addition to directly loading and splitting it, we also did some other test. Is that we have this loading sample, we loaded up, but we didn't load it until it fractures. We stop, we hold, and then wait for a while. The load drops very fast. We wait until the load drops about half of it. Then we keep loading it up, and then then stop, and the load drops because we have displacement controlled. So once we stop our engine, and the measured force drops. So we go several cycles. It's like this relaxation. And we go several cycles of such relaxation test, and we wonder after so many cycles of relaxation, how would this affect our peak force? Very surprisingly, no influence. So this is a relaxation test we did in 2016, and it's a comparison between test number 6, which is a cyclic relaxation loading, and the test number 3, which is direct loading up until failure. So this is how it looks like, as I described. We first loaded up, this is time, and then we stopped our engine, which means that our displacement is fixed now. So it starts to decrease a bit, and then we keep loading up and then until it goes down, and just several cycles, then we load it up until fracture. And then if we plot the force and displacement, then we compare with the direct loading case. The peak force is almost identical. So if my previous slide is true that the loading rate affects the peak load, why not this one? Then this is something puzzling me. And this is the preliminary results, so we are still looking into it. So this is a relaxation test we did in 2016, and it was done with a loading rate of 16 micrometers per second. And in 2017, early this year, we repeat this test. Oh, sorry, I should say that let's look further this image. We just zoom in to see how this relaxation looks like. You see that we almost have the same peak, and also the trend also looks like almost identical, except that we have for this red curve we have some back and forth of this relaxation cyclics. Okay, in 2017 we did the same test, but with a faster speed. This was done with 50 times much faster speed. We load it up and then wait until it goes down. We load it up, wait until it goes down, and several cycles until eventually we load it up until it fractures. And then question again, whether or not this peak force would be the same as direct loading up or not. Again, it's almost the same. So this is the dark curve is direct loading until it fractures, and the red curve is what I just showed you, that we have this cyclic relaxation, and the peak force is almost the same. It shows here. And I think my time is almost here, and I would like to make some summary. Note here that it's not conclusion, because for now, after processing these results, for me it seems that I'm just opening a can of worms. it's just more questions comes into me. And it seems like I can draw really opposite, I can really go opposite directions. First, we can see that at the microscopic level, the crack really meanders and branches. But globally, it seems that the crack has a relatively determined direction to go. And I think this, I have to thank John. John worked out this 2-to-1 ratio, which makes the crack direction relatively more controlled, such that we can capture it by our sensors. And regarding this size effect, it seems that given the loading rate, we did see that the test data is passing through this size minus size, this square root inverse size relationship. But it seems that load displacement is not perfectly linear, and they are time dependent somehow. And also regarding the peak force, it appears to be loading rate dependent, judging from all these tests we find out. But again, if we consider about this cyclic loading, we really wait until it to heal or whatever, to creep or whatever. Seems that it's not influencing the peak load. So these summaries are just opening all these questions to me. What I plan to do is that I would like to find a time-dependent material constitutive relationship and the model to see if I can match my measurement. Okay, I think that's what I want to say. Thank you.
Just on the loading, how well prepared? It's suspicious, the discrepancies, and it kind of reminds me of equipment type issues.
You mean about the stiffness of these things?
Well, and
what discrepancy though?
I can go back to this load displacement.
Well, your conclusion was that, or you were surprised at the result that you had the same or different loading rates, and were getting the same failure peak stress.
Different loading rate seems to give me different loading peaks. But on the other hand, for the relaxation test, we get the same load peaks, irrespective of how much cyclics we are waiting for until we load it until it failures.
Well, the thing I was wondering about was the plates. Like you have this device that applies the load. How well prepared are the surfaces that the plates are pushing against?
Yeah, I think this. I think we have been thinking about that. That plate we have kind of almost rotational wise, it's quite flexible, and also while we were
ball joint behind it.
The plate itself, but the ice surface that it's pushing against. How well prepared?
Every time we try to make the notch where we load our jack, we lift the ice up and we see it's really flat. So that and even Sveinung, I think we are to such details. Even Sveinung was a bit very picky about any bolts that coming out of the plates that he woke up in the very early morning to cut out with those bolts such that we have perfect contact. So in that sense, I think we have a relatively good control.
And the stiffness was 10 tons per millimeter, so and that was measured, not just calculated.
Yeah.
I'm just looking at the data.
Yes.
So at the lowest speed, if I'm looking at it correctly, I'm seeing a peak running from about 12 to 14.
Yeah. Here it's about one is 14, another is approximately 13.67 something.
And the highest is running from 10 to 12.
Yes. And how reliable on this one, I'm not quite sure. Because if I zoom in here, it seems that these are the slow loading curves, and they look quite alike towards each other.
I guess what I'm getting at is the statistical significance of this difference. Knowing how variable our measurements, almost of any kind one makes on ice. There's a number, and then there's a plus or minus some standard deviation, and there's variability. I know you can't go back and do 300 tests, but I'm just wondering how much emphasis I should place on the differences I'm seeing here, whether that's just statistical noise or whether it's physics.
In terms of this field test, we have some repetition, but in the field it's very difficult to have a large amount of repetitions. And I think if we go to this figure, you can see that for each of these loadings, we have approximately at least 4 repetitions. So we hope.
The red one down here, and I see another blue.
Yeah, the red one here, I think it's both from last year and this year. And for this blue and the ducks, they are from this year.
Could you do some kind of p-test on those numbers?
Sorry?
Some kind of statistical test that tells
Oh,
you.
not yet.
Oh,
Now it's a very raw, very fresh data that you're
Between
looking
one
at.
set and, I would do a p-test, some kind of analysis.
Chris? So sort of following up on that, actually, I've done hundreds of loading rate tests with snow samples in bending, and I see the same thing. I see higher peak loads for slower loading rates, and it is consistent and it is statistically significant. And it seems to me that the answer does lie in some sort of, at slower loading rates, you've got a little bit of creep deformation at the crack tip. It's competing with the sort of crack growth, kind of like you described earlier, Erlen. I think that's the explanation for why you're having to put sort of more energy in, because you're dissipating a little more at the crack tip at the slower rates.
Victor?
Well, sort of related to that too, do you know if there is or is not any deformation ahead of the crack tip before your decrease of load?
There is some deformation because we have like 4 gauges ahead of the crack tip. Before before it fractures, we have this loading up, and we obviously see that those sensors, they are also being activated.
There's opening.
Yeah, there was like a displacement.
Not much, but some.
Yeah. That's also the reason we want to use those data to back calculate this cohesive law.
Once again, about this loading rate effect, and in relation with Chris' comment, maybe could you try to quantify on your loading curve the deviation from linear elasticity on the loading part of the curve, and then to try to correlate that with the peak stress, because if you have another mechanism which is not elasticity, like creep or dislocation, plasticity, and so on, should have something which deviates more from linear behavior. So you might try to quantify
this
that.
part of work John has done it in 1998, right? You were trying to use the linear elastic, linear cohesive fraction mechanics to match your result. It turned out the linear elastic is not really matching up.
Not use linear elasticity. You need a viscoelastic cohesive crack model. So you've got to subtract from the total deformations, the creep deformations, and then you can match the fracture deformations. And actually, in my talk tomorrow, I'll show the results of some Arctic and Antarctic tests. That is a preliminary to what Wenjun must do.
So forward in time, we will also bring in a previous experience, and we have a lady here, doctor student at Alto, working with John and myself. We have Yuko in and Wenjun. So we are really, and that's why we have in the upper left corner preliminary results. But we wanted to show them so we can have some discussion around it at least, and then we come back to it.
Very good. Well, let's thank Wenjun and Sveinung for an excellent talk.